Okay, let's prove that for the hexagonal close packed crystal structure that the ideal C to A ratio is 1.633. Why is this useful to us? Well, it's useful because we can use it to calculate the ideal or theoretical density of a um, of a structure made up of all one type of atom. And so what the C to A ratio is it's basically saying if we're given a particular uh, uh, length of one of the sides of the hexagon, what is the height going to be? And it's constrained. This relationship is going to always be somewhere around this value because of the way that the atoms are packed together in a hexagonal close packed crystalline structure. So I made a little graphic here to demonstrate exactly what it is that we're looking at, because it can be sometimes confusing to look at these shapes. So this is the hexagonal close packed structure, and then this is a unit cell showing that exact same structure. Okay, so how do we go about calculating the that value and come up with that same number? Well, the best way to do that is to start by drawing a plan view of the hexagonal structure and kind of work your way through the geometry from there. So if you draw a circle, it doesn't matter what size it is, of course. If you take that circle, and you could do this with a compass, and using the same radius, if you were to draw a straight line first and then draw the first circle so that your compass was centered on that line, you can then, by drawing the exact same radius along that line, let me just draw the line so you see what I'm talking about, you can then get the sides of your hexagon, which would be the intersections of the three circles. Okay. So once you have that, you can then draw circles that represent the atoms, and the atoms are going to have their radius is going to be sort of half the length of that of one of the legs of the hexagon. Okay, so then you can copy those all around. And if you needed to figure out what the midpoint is, of course you can use your compass to get a bisector and create a bisector to cut right through the middle of that. Okay, and when you do that, you're going to find that all of these they're all perfectly tangent to one another. And so that really makes up the lower section of the hexagonal close packed structure. Now the second section, the middle section, is circles or atoms of the exact same radius that are placed in 3 spots, and those 3 spots are right in the middle of these little triangles here. So let's draw just one of them and see where that is. Now, I don't have any geometry on this drawing that's going to allow me to select that point to draw the other circle. So the way to achieve that would be to draw a triangle like this. That's going to the center of our symmetrical structure here. And then if you were to bisect the triangle along any of the sides, because this is an equilateral triangle, then you would find that you could find the center by drawing those bisectors, and that would be the center. So now I can just copy that same radius circle to the center there, and that is where the three atoms in the middle are going to be placed. There'll be one here, there'll be one centered here, and one centered there. Okay, and now we need to figure out what is that. We're going to use this to help us figure out what is the height of C. So this can be kind of hard to look at, but what we want to do, ideally, is find, if we could find the height that we have to raise the middle sphere to, then it's a done deal. So here I've sliced away part of the triangle, part of the lattice here that we've got. And where did I slice it? Well, what I did was I sliced it right through here. And notice that what I've done is I've sliced it right through the center of this circle and this circle right here. And by doing that, I can look at the point at which these two circles are tangent to one another, the point where they're touching. When you do that, you'll see that that this center triangle right here, this is a triangle that's standing up in the z direction, has a hypotenuse whose length is 2 times the radius. And the leg of the hypotenuse is one of the lines that we just drew on our geometry drawing that we just created. And it is this length right here, from this center point to the center of that circle right there. So we have a triangle now that we can calculate the height, half of the height from. But we need to figure out first, what is this length? The length from here to there. And to calculate that, we use this two-dimensional drawing. Because what we can do is draw a line from here to there. And then we know that this triangle right here, let me change the color of it, I guess. Guess I can't really change the color of it that well, but this triangle that's formed by these 3 lines right here has one leg whose length is the radius of the atom. And also the length of this leg is half of A. Okay? So let's go over now and do a little bit of math. So if I were to draw that triangle out roughly, draw that triangle out, then remember that the longer leg is A over 2. I don't know what that side is. And then this is the value that I'm really interested in finding out. And if you go back to that drawing, remember that this is an equilateral triangle that's coming out from the center here. And that means that because we've bisected it, of course, this triangle is a 30, 60, 90 triangle here, with this side being 30 degrees. Okay, so that means we know that the angle here is 30. Okay, and we have the adjacent side, so we have cosine here. Cosine of 30 degrees is equal to the square root of 3 over 2. And so the square root of 3 over 2 is equal to the adjacent side over the hypotenuse. Okay, so A over 2 over x. Let's multiply both sides by x. Okay, so we'll multiply this side by x. And we'll multiply this side by x. And those will cancel out. And we'll get x square root of 3 over 2 is equal to a over 2. And now we'll multiply both sides by the reciprocal of the square root of 3 over 2 so that we cancel them out from this side. So we'll multiply this side by 2 over the square root of 3 over 2. 2 over the square root of 3. And now we see that, because the 2's cancel out, that x is equal to a over the square root of 3. Okay, let's go back to our drawing, our model really quickly, and just take a look at what that tells us. We'll take a look at this 3D image here. And this triangle that's standing up here we don't know what the angle of, we don't know what any of the angles in this triangle are. They're not necessarily nice angular measurements. But we know that this lower side, we just calculated that lower length. And we know that the hypotenuse, because of the way that we were looking at this, the hypotenuse is 2 times the radius. Okay? Which means that it's also a. Okay, so we can look at it either way. So let's go back to our drawing now, and we'll draw that triangle and solve for that triangle. So that triangle, let's just draw it sort of as it was standing. We had it like this. Okay, and we had calculated this value here is the lower part, so a over the square root of 3. And this side we said was 2r, but remember that 2r is also a, right? Because those are the little radiuses right there, or radii. Okay, so that's a. And this is half of c. So once we know this side here, we can multiply it by 2 and find c. Okay, so the way to solve this, of course, would be to use the Pythagorean theorem. So a squared plus b squared equals c squared. We know the hypotenuse we're looking for, one of the sides. So let's plug in first, and then we'll rearrange our terms. So we have c over 2 squared plus a over the square root of 3 squared equals a squared. We're trying to solve for c, so let's move the a over to the other side. So we get a squared minus a over the square root of 3 squared. And that would give us that this is equal to c over 2 squared. So we'll take the square root of this, and that equals c over 2. So then I could multiply both sides by 2, and I would get c. Okay, so then when we do this, we'll get, let's distribute the square into this fraction here. So we get 2 square root of a squared minus a squared over the square root of 3. And, oops, I'm sorry, that's not the square root of 3. A squared over 3. So now we can combine terms here by multiplying this right here by 3 over 3, which is just 1. And we get 3a squared over 3 minus a squared over 3. So now we have common denominators. We get 3a squared minus a squared, which is 2a squared over 3. And 2 times the square root. That equals c. Okay, well, we can look at this as really as 2/3 times a squared underneath this radical here. And then we can just say, we can pull the a out from underneath the radical and get 2a square root of 2/3. And then c over a equals 2 times the square root of 2 over 3. Okay? And if you punch that into a calculator, you will find that it equals 2 times square root of 2 divided by 3, which is 1.62. I'm sorry, 1.6329, or 1.633. Okay, and again, the point of this, knowing this number, is that it's very useful for calculating the density of a particular crystalline structure that's made up of a single type of atom. And here's how you can use it. Okay, this equation right here will allow you to just plug in the radii of a particular atom, and it will spit the the hexagonal close packed volume out for you. Okay, and so what all this is this is the area of a hexagon. This is the area of the hexagon. Okay, which is 3 square root of 3 divided by 2 times t squared, where t squared is equal to the length of one of the sides. Okay, and there's our t squared, it's 2r. Okay, and then we multiply that times our a times 1.633, and that will give us the volume, because that's length, or that's the area times height. So area times height gives us volume. Okay, and that'll be useful in other types of equations that we'll have to do later on. So I hope that was helpful. Enjoy.